Hello, today I'd like to talk about reinforcement learning. Today's class objective is that I'd like to introduce the basic concept of the RL techniques. The topic of the RL itself is very broad, so we cannot cover all of technique within this class time, but I will only touch on some of the basic concepts. Before we move on, last time we also talked about RLT techniques that are main designed for handling single query, and also we also talk about this keynote dynamic planner. This showing that is the branch of the machine learning. So basically, I assume you know some of the basic concept of machine learning related to the supervised learning, also this unsupervised learning, and maybe seems like some of you already know some of the concept of the reinforcement learning. Also, I found that the slide of this David Silver is very good on the topic, so I will give my lecture based on his slide. So basically, one of the main branch of the machine learning, also this reinforcement learning. Reinforcement learning has a very interesting concept. So basically, these are some of the main components that set apart this reinforcement learning from other machine learning techniques. So basically, there's no supervision, there's no supervisor. Instead of we have this supervision, there will be another this supervisor information. This reward signal reward. So basically, RL actually works along the concept of reward. In a way, this reward is kind of the supervising information. However, we may not get this reward immediately. So in most of case, we do some action for the RL along the RL for achieving some task, but we might not get a reward immediately. But instead, we might get that kind of this reward feedback a long time later. So in other words, this feedback is kind of delayed. So we should have the mechanism that once we got this delayed feedback, we need to associate because of what action we get that this delayed feedback. Also, this time really matter in the RL case. So basically, in the RL case, we take some action and we got some reward and observation, and then based on that, we take another action. Overall, we want to achieve this accumulated reward by taking a series of these actions. But as you may know, in a lot of machine learning, also there are a lot of the statistics concepts. We assume this IID concept. But since actually as you can see in the RL case, we take action and reward which actually correlate each other. So basically, there are actually a series of the action and reward. So basically, we cannot have this kind of IID concept. So this actually makes a lot of this technical challenging. And also as you can see, basically the RL here we assume the agent takes some action, and then due to this taken actions, it affects the subsequent data we can receive. In other words, there are actually some of correlation. So this issue also related to the time really matter. These are actually some of the characteristics, also the technical challenges that we need to concern for performing this reinforcement learning. These are some of the examples of the RL techniques. So, for example, we can design some of we can design the flight stunt maneuver in a helicopter. We can actually think about it. What are a series of actions to do that? Also, we can design some of the planning algorithm to make the humanoid robot walk on an arbitrary path. Also, there can be many other related ones. As you can see, the RL actually they're concerned about this reward concept of reward. The reward is kind of a scalar feedback signal, and it indicates how well the agent doing at a particular step by taking some action or not. Also, basically the main goal of this RL is that basically we want to maximize the cumulative reward. It means that we take some action, we got the reward, right? And next time we take another action, we got another reward, right? Basically, overall, we want to sum all these reward. In other words, we want to maximize this cumulative reward. And then basically this RL technique based on this reward hypothesis. So basically we assume that all goal can be described by this maximization of the expected cumulative reward. So basically the concept of a reward in RL is actually very, very important. But depending on your cases, sometimes actually we can it's very easy to get this kind of reward. But in some of the tests, we might not get the direct reward. So then we need to think about it. In what way we can get the appropriate reward. And then I talked about the fly stunt maneuver in the helicopter. Then at that case, we can give the positive reward for following the desired trajectory. Also, there we can give the very negative reward for crashing, since we don't want the crashing, right? For the human robot case, we can give the positive reward for the forward motion. Also, we can get this negative reward for falling over, since we don't want that. We don't want that kind of that kind of the falling over on the ground. Basically, these are some of the we can actually design the reward for that to achieve this kind of task. R is in a way sequential decision making. So overall, we want to select a series of actions to maximize this cumulative reward or total. In other words, the total future reward. And again, this action might have the long-term consequence, right? Again, the reward may be delayed, and then further, depending on the cases, it's better to sacrifice immediate reward to gain a more long-term reward, right? So it's actually non-trivial to think about it. What might be the immediate reward, and so what might be the long-term reward, and then what kind of action we have to take, right? So basically, as you can see, a lot of that also our activity in even our real life actually also related to this kind of sequential decision making, which is actually RL actually focus on. And then sometimes actually we can have this kind of we can sacrifice this immediate reward. For example, instead of keep moving helicopter going on, we can take the action of the refueling helicopter, which might prevent a crash in several hours later on, right? Also, in common games, it's very common to blocking opponent's move, which can have the winning their chances maybe many moves from now on, right? So instead of attacking directly the opponent, we can take this kind of the blocking operation, right? But always, when you think about it, what might be the best move, depending on the cases, right? So basically, in our case, we need to. These are the two common concepts here: agent and environment. I also use the concept term of agent before. The agent is that somehow at this time step t, the agent, basically RL agent, received observation OT from the environment, right? And then also we receive the reward. And then based on our observation and reward, we take the action that may lead to better reward later on. And then we take the action, right? Then environment actually give us receive the particular action that we take there, and then it emits the observation. Also another scalar reward for the next time step. And then we keep doing that, right? By incrementing this time t. This is actually basic context for the RL. And basically, we can think about history, right? History is nothing but a sequence of observation, action, and reward, right? We receive observation at L time t, reward, and take the action, and we keep doing that, right? And then basically, our next action should depend on the history, right? But basically, in other words, this is state. We use the term of state, which is nothing but information used to determine what happened next, right? And state is nothing but this history, right? So formally, the state is nothing but a function of history. We somehow get some representation that summarizing this kind of history. Sometimes we can directly use this history, or we can have the more better compact representation. Typically, we can use some recent deep learning representation for doing that. But anyway, state actually there's nothing but this kind of history. But you might heard about this Markov state, right? Markov state, or some people say that is an information state. So instead, basically this is actually a state is the Markov if and only if. So basically, there's certain probability transition. Some of the probability transition between the state, given this, given the history of the S1 to the ST, and then basically when you think about it, what's the probability of having the next time step ST plus 1? Then basically next time step only depends on the just the immediate prior state ST. It means that future is independent of all the past, given the current, given the present state, right? This is actually when we have this kind of equality, we say that this is actually Markov property, and a lot of cases we assume this kind of the Markov property, Markov state. And then once this current state known, then we can actually we can throw away all the prior history. Then this will simplify a lot of our overall process. Also, there are many other major components of the RL technique. So there will be the policy for the RL agent, policy, value function, and model. When you read some of the recent paper about the RL technique, these are actually very common terms. Policy is nothing but agent's behavior function about the action, right? And then value function is how good is each state or the action. I mean, obviously we need to have a certain measure of how good the action or state will be good, right? So that's why that's the value function. And model is the agent representative of the environment, right? Also, we can think about we will get the sum of the observation, right? And then we can use some of the deep learning representation or some other representation of that compactor represent that kind of environment. These are the some of very basic concept about the RL agent. And policy, again, it's a map from state to action, right? So there are two different one determines the policies that at a given state, if we know our current step, we can define there will be always this determines the policy action. Then this actually determines policy. But a lot of cases we use this kind of stochastic policy. In other words, we will use this kind of probability distributed function. Given the current state S, and then there will be this probability distributed function of taking a set of actions actually. Then value function is a prediction of future reward, right? So again we use this value function to evaluate the goodness of the state, and then basically by utilizing this value function we can choose the particular action to maximize this cumulative future reward. Here, this given state, we will get this direct reward, right, at the next time step, and then also we take another. Basically, we can take another action depending on the chosen policy, and then we will get another reward, right? But actually, the future reward, basically, we can get the $100 today, but also we can get the $100. Also, you can choose to take the $100. You can choose to receive $100 today, or you can choose to receive the $100 tomorrow. Which one do you prefer? Probably most of us prefer to take the $100 today, right? But there are some people may want to have this long-term view, and then they might be also if there's a chance to get if there are chance to receive more reward in the future, some people may take that action, right? But in other words, $1 today and $1 tomorrow, actually they are not equal. They may not be equal value. So that's why further future reward, we take some of these kinds of we use this kind of discounted weighted to adjust to reflect the future value to in the current context. So and then we actually keep doing that until for the future one. So basically, this value function is nothing but expected value of this cumulative future reward. And then I don't know, I haven't played this game, but basically this showing a series of frame, and that at that frame we are showing this reward function. Somehow this one shoot the missile toward there, and then it looks like it's highly likely to get a better score. So that's why actually we got the better higher the value function and so on. Another one is the model. Model is nothing but predict what the environment will do the next. What are factors about the environment? You might recall that basically if you take the action the environment should give the observation, also give us this next state, right? The P predict the next state here. So basically the probability function given the current state under also by taking a particular action A, one might be the what is the actual probability to have the particular state next time. P is actually the one of model. Also R predict the next immediate reward, right? And then given the current state action, one might be the immediate reward at the next time. The PNR function is the typical component of model. And so far I talked about, I explained that some of the concept, also the term. Here I give the very simple maze example. Here we want to, there's some maze, this is environment, and then we want to move from here to there, right? And then here the reward, we set the reward in a way to take the -1 per time step to reach the goal. So obviously we want to maximize the future cumulative reward, right? So in other words, we want to take the smallest step to reach the goal from the start to maximize this reward, right? And action is that we can this north, east, south, and west move, right? And then step is nothing but this the agent location. And then basically we can see this here we can have this kind of policy. Here at this basically at this state at the current location we take this in this case take this east of action. Here we take the north we are moving we taking the north direction. In other words, here at each state we only had this predefined deterministic action. So in other words, it's actually the deterministic action. And here also we are showing the value function. Here at that location, by taking only one action, by going there, here by taking this action, we can reach there, right? So as a result, we got the we only get the reward of -1. Here -2. You can actually think about this one might be value function at that step. And also there are a lot of cases actually we are using this value action value function, also known as this Q function. It's nothing but expected return starting from the state S by taking action A. The basically expected function from the state S and action A, then following the given policy, whether this weighted function as a discounting factor. And then basically the one might be this expected return, expected cumulative reward, right? So it looks like it's very similar to the value function, but also here actually we also consider this action together. And this actually gives us the goodness of the state given by taking the particular action A. So far I talked about the main concept of this RL. So you might have one might be the difference between the learning or planning. The planning nothing but so far we talked about a lot of these motion planning techniques, right? And these are actually the two main approach of the learning and planning for sequential decision making. You know, in this class we are talking about this path planning. Path planning is also the one of the example of the sequential decision making. And in the case of the RL, the environment initially we don't know the environment, right? When we need to interact with the environment, right? The agent need to interact with the environment, and we observe something. Also, we get the reward, right? By going through a lot of the interaction, we can improve we can understand what might be the model of the environment, and then based on that we can what might be the reward, and then based on that we can improve our policy, right? So in other words, this RL kind of takes the trial and error approach. On the other hand, planning is that when I talked about the planning, roadmap and RRT, basically we assume that environments are already known, right? So basically we assume that there will be a triangle or the octomap or the point cloud about environment map, and then we can do the coordinate detection, right? So the model is the given, and then also the agent perform the computation. We do a lot of computations with this kind of known environment without we don't do the external interaction in a way, right? We know that one might basically we do some operation for performing collision checking, right? We know that in what case we have collision, or so in what case we don't have the collision, right? So that's the kind of computation, but basically we only know we do the very simple computation instead of the interacting with environment to understand this environment, right? We already know the environment. But based on that, the agent can improve each policy, right? Basically, we can compute the better path. We can optimize the path by doing some of the actual reasoning or there's some sort of the analysis or the search, that kind of one. So basically, the reinforcement learning and planning aims to the same goal. We want to achieve we want to compute the path given the sequential decision making, but approach is different, right? Sometimes actually I think that sometimes if the environment is known, we can use maybe we can use this kind of the planning technique, right? Since we don't need to we don't need to interact with the environment, right? But a lot of cases we know the environment, but some of the information is not known. For example, here actually so before I talked about the sensor, talked about the sensor noise, right? Basically, initially we don't know what kinds of the noise or also what kinds of error the sensor that we are using will have, right? So at that case, we can actually assume some of the model, right, about this noise, right? We can assume some of Gaussian noise, and then based on we can do that. But the assumption may be wrong. The assumption may turn out to be wrong in the practical cases, right? At that case, probably we can use this kind of RL approaches, and then we can also we can interact with the environment, and then we can observe actually some of the noise model and so on. So I think that there are a lot of interest about the RL technique, but I believe that there are a lot of room that we can actually using them, we can integrate them together to design the hybrid technique to handle a set of these diverse problems. And again, in the case of learning, basically even the rule of the games are unknown, right? So in some of the cases, for example, here we want to design RL agent to play this game, right? Even the rule is not known, and then we need to learn those kinds of rules by having some interaction with the environment, right? And then we take some action, we observe something, and we got also reward, and then we pick the action on joystick here in this case, and see the observation in this case pixel image, and we keep doing that and keep doing that. Also there will be the score. Then we can interpret them as this score number as a reward, right? And then by doing that, actually, we can also we can compute the policy that can maximize this kind of score. This exploration and exploitation is a very important concept across the planning and learning. Again, in RL, basically it takes the main idea of the trial and error approach, right? So basically, agents should discover the good policy by having interaction with the environment, but along that line, we don't want to lose too much reward. Also, we want to learn the process in an efficient way, right? We don't want to spend a lot of time. And basically, the exploration is that we somehow take some action so that we can gain more information about the environment, right? But sometimes we get some of the environment, we get some of the observation about environment, and then we want to exploit. We want to take this exploitation. Exploitation is nothing but we want utilizing this information to maximize the reward, right? So, for example, this example for the game playing, exploitation is that play the move that you believe the best, right? You keep doing that, right? But sometimes there might be better move, right? How can you learn that better move, right? Then you need to do this exploration. Play an experimental move, and then you do that, and then you observe the reward, right? But by doing that, you can learn something better one, right? Always there is actually the dilemma of utilizing your time for the exploitation, also the exploration. Same thing. Even for the motion learning, we have also the same problem, these issues. Some of there has been a lot of the research going on, but one of the seminal techniques, DQN, Deep Q network. It's nothing but utilizing this Q learning. So before I talked about Q function, right? So here actually we want to model this Q function, this action value functions. So basically we want to know the value function given as and taking the action, And then we do that. We utilize the deep learning to understanding, to understand this observation state. Also, what are actually the reward function given that one. So we use some of the convolution neural net or dense layer about there. And then also it has basically it is one of the early this end-to-end this RL approach. Also, it used there will be a lot of issues, but also it stabilized the training with the experience replay buffer. This is nothing but basically we taking a lot of we take there a lot of interaction with the environment, right? We take this action, we got reward, and we keep doing that, right? And then it gives us a series of the action and the reward, right? We store that information into the experience replay, and then we replay that experience. But actually, instead of the sequentially replay those experience, we randomly sample them. Basically, we take the certain sample and we take the sum of the sample of taking action, reward, and so on. Why we are doing that? So it has been known that by randomly sample those actions, we can actually break the correlation between the consecutive samples, right? Since actually a lot of machine learning, also a lot of this learning technique assume the IID cases, right? So yeah, basically under the IID assumption, we don't have any correlation. But experience that we achieve through this interaction under this RL it does not satisfy the IID concept. So as a result, to break the correlation between the sample, we take this random sample approach from this kind of experience replay. Also, there may be many other advanced techniques, but I recommend you to go over those papers if you're interested on them. And today I talked about some of the basic concept about the reinforcement learning. Of course, actually, the RL technique is much more broad, so that I cannot cover all of them within this lecture. So, if you're interested, more detailed lecture available under the topic from this David Silver. I strongly recommend this lecture material to you. Okay, so far I talked about some basic concept of RL, and then basically you don't need to do the you don't need to do any more the paper summary submission. Also, you can only you can submit this last question today, but you don't need to submit any more question from the next week. And so instead, I recommend you to browse some of recent paper, and also and then you need to focus on the paper presentation, also your this project progress. So that's it. So yeah. Thanks so much, and I wish that you follow some of the also for the midterm exam. I'm not going to make the very difficult question. If you follow all the lecture material up to this material, then you are ready to take the midterm exam. That's it. Thanks so much. Bye.